Okay, this time we don't have any numbers to check. We only know the KSP value, but from KSP we can calculate the solubility. One word of caution I will tell you as you're doing problems for KSP, these variables or these values vary greatly. So make sure that if you're doing book problems, you're using the KSP table in the back of the book. It's on A-8, and there's some smaller tables within Chapter 19, but the big table's on in Appendix C, A-8. So first thing you're going to have to do is write a balanced equation, as always. Okay, and iodate is like chlorate, so it's IO3 negative, and since it's copper plus 2, you have plus 2 ions and iodate ions. Again, the solid is not part of the equilibrium expression, so you're going to get X for the copper 2 ions, and you're going to get 2X for the iodate ions because you get twice as many iodate ions as you do copper. So substituting that into your KSP value, it's going to be Cu plus 2 times your IO3 concentration squared. So 1.4 times 10 to the negative 7th equals X times 2X squared, or 4X cubed. Okay. So you'll need to divide both sides by 4, and then it's the cube root of 3.5 times 10 to the negative 8th. And you should have a cube function on your calculator. If not, above your y to the x, there should be an x to the y key, and you can take any power from that. So x is going to be 3.3 times 10 to the negative 3rd. And again, that's molarity moles per liter. Okay, you can use KSP values to compare the solubilities of different solids. So this gets into explaining why some things are slightly soluble on your solubility rules. For these, all of these compounds have the same number of ions in their formulas, and I'll show you why these are the same then with the calculation. So I'm going to write out the equations for each one of those. I know I didn't leave you a whole lot of room for this, but just so you get a visual for why this works the way that it does. Okay, after writing out all of the equations, you'll see that each of them give you a value of x and 2x, which then goes into your KSP value as x times 2x squared. Again, calcium hydroxide and barium fluoride are most similar. So again, x, 2x, exact same expression, just being divided into different numbers. Silver chromate gives you the same number of ions. This time the 2 goes with the silver instead of the chromate, but you'll see in each case you're going to get 4x cubed. No matter what you're using. So since these expressions are all the same, you can compare the numerical values the same way. For the KSP values, you can compare them the same way as you would here. So you can see that the largest solubility is going to be the 6.5 times 10 to the 6th. Which makes calcium hydroxide the most soluble. Barium fluoride is next with 1.5 times 10 to the negative 6, and silver chromate is last with a KSP value of 2.6 times 10 to the negative 12. And these solubilities would be the X factors in each of those calculations. So again, you see those numbers are going to follow the same pattern. Solubility of calcium hydroxide is the most, barium fluoride is next, and silver chromate is last. Okay, if the number of ions is different, solubility must be calculated. So we have the KSPs for 3 different compounds, and if you just look at your numbers, you might be able to get the iron hydroxide or ferric hydroxide one correct, but you probably wouldn't get the that silver sulfide is more soluble than CuS. This you do need to do the calculations of the solubilities because the number of ions are different. So again, you're going to be writing equations and solving for X in the KSP expression. So I'm going to pause the video, please, and do that calculation. So for the first one, copper 2 sulfide, you get 1 ion of copper 2 and 1 ion of sulfide, each one being X. So the square root of 8 times 10 to the negative 4th is your solubility. Again, molarity. You'll notice again these do not have a lot of sig figs. It's very hard to measure these concentrations, so they're not very significant. So again, you will see widely different KSP values for that reason. So again, as you're doing problems, make sure you're doing the KSP values given in the book to be able to compare your answers to the answers in the back of the book. Okay, I'm going to continue with the other two. So again, you can pause and write those. Okay, for the silver sulfide, you get 2 ions of silver and 1 ion of sulfide. So you're going to see the expression 2x squared times x for that, and that gives you 4x cubed when you put that together. Again, so I'm looking here. So this is 2x from the silver ion, x from the sulfide ion. Simplifying that gives you 4x cubed. So again, dividing 8 times 10 to the negative 48th divided by 4 and taking the cube root of that is 1 times 10 to the negative 16th. Again, if you're having trouble with a calculator trying to figure out how to do the roots, please either check with your math teacher or go online and search for the manual. I did find the manual online, so if you don't know how to do that, it is available online. Just search cube roots on a TI-83 plus or whatever calculator you're using if you're having difficulty with the math portion of this. And then for the ferric hydroxide, you have 1 ion of iron 3 and 3 ions of hydroxide, so you get x times 3x cubed. Simplified gives you 27x to the 4th, so divide 1.6 times 10 to the negative 39th and take the 4th root of that, and you get 8.8 times 10 to the negative 11th. So from your solubilities, it's very easy to see that iron hydroxide is the most soluble, so it has the largest number. Okay, the silver sulfide is next. Even though its KSP value is lower, its solubility is greater than that of copper 2 sulfide. So again, if the ions are different, that's the key. You need to calculate solubilities and can't just compare the KSP values. Okay. Common ion effect is another application of Le Chatelier's principle, so it works the same as it does in any other equilibrium system. The solubility to solid is lowered if the solution already contains one of the ions that are in the formula. So this is going to be, again, in equilibrium with like an ice chart. So I'm going to write the balanced equation and start the ice chart. Okay, so you'll see CaF2 breaks down into calcium ions and fluoride ions. So if you're putting it into this 0.025 molar sodium fluoride solution, again, that one is completely soluble. So you're going to have 0.025 molar NaOF and basically 0 of the calcium. So we're going to expect the equilibrium to shift to the right. Again, the solid's not applicable. Okay. So again, these never appear in your KSP values. So the shift is going to be to make more of this and 2x of the fluoride ions. So since we know the KSP value, okay, it's going to be the calcium ion concentration plus the fluoride ion concentration squared. We're substituting what we have in is 4.0 times 10 to the negative 11th. Equals x times 0.025 plus 2x squared. So again, just like we had in other equilibrium problems, the 0.025 compared to what the value of x is going to be small. So this KSP is a very small one, so we're going to eliminate x. So x is small in comparison. Okay, so it's that addition rule. It's not significant in comparison to 0.025 molar. So we're going to drop that function here, and basically we'll have 4.0 times 10 to the negative 11th equals x times 0.025 squared. Okay, and when you simplify all of that, x is 6.4 times 10 to the negative 8 moles per liter, or molarity. Okay, All right, this concludes problems or page 1, so you should be able to work on problem set 1, page 850, 70 to 80 even.